So a few of my friends were trying to solve a problem on a coding platform a few days ago. They were stuck on it for quite a while, so we decided to discuss the problem with y'all. Basically, it involved 3 singly linked lists that were already sorted. They had to merge them and return the new list in a sorted format. So let's take an example for it. The sample input is 1, 3, 6, 4, 5, 8, 9 and 2. A linked list can also contain a single node as we know. Now, the expected output is 1, 2, 3, 4, 5, 6, 8, 9. As we can see that it is nothing but a merged and sorted list in ascending order.
To understand the problem clearly, let's see the problem through a different perspective. Let's consider those individual lists as some stack of blocks, each of them already being sorted, say on the basis of their width. And now, to get the desired output, we can merge these blocks to make a huge tower. So, to achieve this, we can just stack these 3 stacks, one over the another, and then sort them in the ascending order by swapping them. Now, it's sorted as required by the question. So basically, what we did here was, in terms of the list, is concatenate the 3 lists and then sort them in ascending order.
Yeah, this solution is good and gets the job done. But I guess that this approach is pretty unoptimized. Like say, if we consider 4 lists, 5 lists, and then eventually n lists, and then concatenating them all at once, and then sorting them is pretty slow.
Yeah, exactly. That's why let's consider 3 sorted stacks of blocks separately, as they were before, and keep on comparing the sizes of the topmost blocks from each stack. Let's say we compare these 3 blocks. As we can see, the size of the first block is less than the other 2. We place it in the new list. Now we compare second block from the first stack with the topmost block of the other stacks. Here, the size of the block in the third stack is less than the other 2, so we place it in the new list. Now, we are left with only 2 stacks. However, if the third stack had more than one element, we would have compared it in the above fashion. Now, in this way, we arrange all the blocks respectively. Now, all the comparisons are done, but we are left with 1 stack, so we would append it in the end.
Okay. I can do one better. Instead of considering 3 stacks, we shall consider 2 stacks at once. Because let's say if we have more than 3 stacks, then comparing all of them at once will be quite tedious. Now we compare these 2 stacks in the same manner as Margashi explained and create a new stack. Now similarly compare this new stack with the third stack of blocks and finally get the required stack, aka the sorted merged list as required.
So now that we have properly understood the question and a simple but elegant approach to it, now let's figure out the time complexities of each approach.
But I guess before that, let's briefly understand what exactly time complexity is. Time complexity is generally denoted by big O notation, which is a term used in computer science to describe the performance of an algorithm. Big O specifically describes the worst case scenario and can be used to describe the execution time required by an algorithm.
Yeah, so big O of 1 or simply O of 1 implies that the algorithm takes constant number of steps for execution. Example, checking which number is greater among the 2. Similarly, O of n, that is linear time, requires in the order of n steps, where n is the number of elements in the list. Similarly, we have got O, log of n to the base 2, which is obtained during binary search, as we simply keep on dividing the problem into half at each step, that is, it is O of log of n, and O of n square, which is obtained during bubble sorting, and so on. We have got O n log n, exponential time, etc.
Oh, so that is why the very first approach requires almost O of n time complexity for concatenating, and then in the best case, O of n log n for sorting, which is pretty costly in terms of processing if the data is huge, which normally is in real life problems. Okay, too much of talk. Now let's get to the fun part.
Now, let's discuss the flowchart for iterative approach. Here, we pass heads of both the lists to the merge function as h1 and h2. Now, we compare if h1 equals null. If this is true, we return h2. Else, we compare if h2 equals null. If this one turns out to be true, then we return h1. If both the conditions turn out to be false, we check if either of the lists gets exhausted by checking if their head reaches null through a while loop. Here, within each iteration, we compare the value of the data fields and store the smallest among them by creating a new node in the resultant list. After that, we increment the respective head by allowing it to point to the next element. In this way, we iterate until either of the lists gets exhausted.
Now, in the second part, we check if h1 equals null. If yes, we check h2 equals null or not. If no, we loop until h2.next equals null and add h2's data to the merged head's data at the end of the loop. Inside the loop, we add the data from h2 to our new list and increment the pointers to both h2 and the list. Similarly, we check if h1 equals null. If no, we loop until h1.next is null and repeat the same operations that we perform with h2. Now, once both these conditions are true, we return to the point result and end the program.
First, let's discuss the iterative approach. At the very beginning, we declare the abstract data type, that is the ADT for linked list. After that, we implement the basic linked list insertion at the end, where the user passes the value to be inserted, for which we create a node, then store this value in its data field and increment it. Similarly, we also declare a traverse function to which the user passes the head of the list, so that using it, we traverse through each node in the list and print its data field's value.
Now, within the main function, we declare head1, head2, head3 as heads to the three given sorted lists. And for the sake of explanation, we ask the user to enter the required list in a sorted manner as given in the problem statement.
Now we pass head1 and head2's address to the merge function, which gets stored within h1 and h2 in the function body. Now we create a new merged head, which is the head of the merged list, and also store its address beforehand so that it doesn't get lost. Initially, we create one empty node.
Now, we keep on iterating over the elements of the linked list until either of the linked list end is reached. Within each iteration, we check the data fields values of each node. If a node from H1 list has higher data values, then we store it in a new node, then create a new one for the next iteration and increment the merged head pointer. In this way, we iterate over all the elements. However, in the last iteration, we avoid creation of unnecessary node.
Now, as the while loop gets exhausted due to either of the list's head pointer reaching the end, we append the remaining list to the end of the new list and finally return its head to the main function. Now, again we pass the returned head and head3 to merge function, and finally its returned value is passed to the traverse function through which we print the entire merged and sorted list.
We can also obtain the same result using a recursive approach whereby we reduce the number of lines of code significantly. Here, we declare the same merge function passing same parameters to it. Firstly, we check if either of the lists are empty or not. If yes, then we return the other list.
Then we compare the data field values of first nodes from both lists. If say h1's data value is less than h2, then we recursively call merge by passing it h1.next and h2 and assign it return value to h1.next. Then say in the next call h2's data is less than h1. Then we again recursively call merge by passing h2.next and current h1. Finally, when we reach the base case, we return the respective pointer. This way, all the nodes get linked correctly and finally we return it to main. We repeat the same process as we did earlier for the iterative approach.
Now, let's see the code in action. Now, let's walk through the code for the iterative approach. Now, we run this particular program And now we ask the user to input the elements of the first list. Here is the print statement for that thing. Now we enter the elements of the very first list. Similarly, we input the elements of the second list. And finally, the third list. Here are the statements where we ask the user to input those particular elements into respective lists. Now, we pass the head of the very first list to the traverse function and print the first list. In the same manner, we print the second list and the third list. Now, we pass the head of list 1 and list 2 to the merge function. The return value is stored in merged head. Now again, this merged head along with head of the third list is passed to the merge function, and finally, we print the merged list.
Now let's see the code execution for the recursive approach. We ask the user to input the elements for all the three lists. Here, we ask the user to input the elements of the list 1. Similarly, for the list 2. And for list 3. Now we pass the heads of all the three lists through the traverse function. Now we pass the head 1 and head 2 to the merge function, and then we pass the resultant head and head 3 to the merge function. Then we pass the resultant head to the traverse function and print the final merged list.
Now, let's revise what all we learned till now. Basically, in the very beginning, we understood the given problem. We discussed about a naive approach to it. Then, we got to an optimized approach. After that, we compared the time complexities as to which one turned out to be more efficient, and then we understood the code algorithm. And finally, added more depth to our understanding to the visual flair.
Bye.